Girls, I'm back with a few more explanations with the remaining problems on the forces practice tests. Um, the one up on the screen right now is number 3. This is another friction problem. Again, hopefully you're starting to see a pattern. The first step in solving any force problem is to draw a free body diagram that helps you see the forces that are acting and try to get an understanding of the way you think the acceleration or what you think these forces will do to the motion of the body in play. Um, this one we've got a block on a surface that's got a friction. There is friction on this surface. So I've put in the pushing force that's acting on the block as well as the friction force. I'd like you to also note that I've intentionally made the weight force less than the normal force because I've done enough of these problems to see that if I have a downward push on the block, then the normal force has to be the sum of the weight force plus this vertical component of the pushing force. So we'll see that in a minute when we look at the sum of the forces, or Newton's second law, in each direction. So if you come over here to step 2, you can see the next step after the free body diagram in any force problem is to write the Newton's second law equation. Because I have to look at some forces acting in both directions, in other words, I need to know what the normal force is in order to find the friction force, I've written the second law equations in each direction. So in the x direction, I have the x component of the pushing force, and I have acting opposing that is the friction force in the other direction, and that's equal to the mass times the acceleration in the x direction. In the y direction, I know there's nothing in this problem that says the block is floating away or crunching into the ground, so I know that the sum of the forces in the y direction must add to 0. So I've got the normal force, the weight, and the y component of the push, as I mentioned to you earlier. Solving for the normal force, which is something that we need in order to find the friction force, I find that the normal force equals 76.5 newtons. Now that I have that, I can plug that back into the equation I wrote for the forces acting in the x direction. So step 3 is solve for the acceleration using that net force equation. And I get that the acceleration, plugging in all the information I know, I'm solving for that acceleration there, and I get that it's equal to 8 meters per second squared. The next question is similar again to the one we discussed today, October 30th, 2017. Again, you can see this is a type of machine called an Atwood machine. Essentially, it's a type of apparatus that's used where you've got a weight and then you have a counterweight to modify the acceleration of the system. So hopefully you can see my amoeba that I have drawn around the system, and that's what I recommend. That's how I recommend approaching this problem. I find this much easier to kind of visualize in my brain, I suppose. So I'm actually finding part B of this question first, which is the acceleration of the system. So what I did was I wrote the net force for the system, and that means I need to consider the whole 7 kilograms of mass that's being accelerated here. Because there's no friction in this pulley, I can do that. And so what I find is that the net force on this system is the difference between the two pulls. I've got a bigger pull in this direction than I do in this direction. So the difference in those two pulls is the difference in the weights of the two blocks that are hanging there. And so the net force is equal to the mass of the system times the acceleration of the system. Solving for that acceleration, I get 4.2 meters per second squared. Now that I have that, I can look at one of the masses individually and solve for the tension force, which is what was asked in part A of this question. So I picked the 5 kilogram mass, but you could pick either one. And I wrote the sum of the forces. The net force on the 5 kilogram mass is the weight minus the tension. So there's the weight minus the tension, which is what I'm looking for, and that's equal to the mass of the block times its acceleration, which we already solved for was 4.2 meters per second squared. Solving for the tension, I get 28 newtons. And finally, the last question was the roller coaster question. Here I've got a roller coaster on a 42-degree incline, and first I'm supposed to draw the free body diagram. So again, that's always step one in any problem involving forces, and I think you should get in the habit of doing that all the time. The net force on this cart or this roller coaster car is, if you look at only the purple forces, you've got the weight force acting downward, and you have normal force acting perpendicular to the track of the roller coaster. You can see that I kind of completed a parallelogram here and discovered that the net force, the diagonal of the parallelogram, is acting acting parallel to the track. Hopefully you saw and recognized that that force must be the x component of gravity. Remember that on an incline, gravity has to be kind of acts in two directions. There's a component that holds the roller coaster car on the track, that's the y component, and there's a component that makes it accelerate down the track. So those two components, which I've shown in green here, add together in a vector method to give me the full weight of the roller coaster car. Also recall that if I know the angle of the incline is 42, then I know the angle between the weight of the cart and the y component. So the next step is to write Newton's second law in the direction of the acceleration down the ramp. By the way, I'm sorry, that's my dog Harry barking. He needs his dinner, so I apologize for that. Anyway, back to the problem. Solve for the acceleration down the ramp, and we get the net force. The only force acting on the car is the acceleration due to gravity in the x direction, which is mg, the weight of the cart, sine theta. So it's this component right here. And we set that equal to the mass times the acceleration of the cart. And notice an interesting thing is it doesn't matter how heavy this car is. I don't need to know the mass of the car because the mass cancels. In other words, the acceleration is just the component of gravity in the direction of the track, parallel to the track. Solving for that, I get 6.6 meters per second squared. So hopefully that helps you understand these problems a little better, and if you have any questions, don't hesitate to stop by or shoot me an email. Have a good evening, and I will see you soon. Bye.